In 7.5, we are going to talk about operations with matrices. So we're going to look at adding, subtracting, and multiplying matrices, and then again, another way to use these matrices to solve systems of equations. So what we're going to learn is decide whether or not two matrices are equal, add or subtract, multiply two matrices, and then use the matrix operations to solve applications. So some of the fundamental theories of matrix is it's standard in math to represent matrices in any of the following ways. So if you see a capital letter like A, B, or C, they may be talking about a matrix. If you see this matrix notation where you have the subscripts, then that can also be the matrix. Or you could just have it in this third notation where you kind of have a little bit of everything. Matrix A is the matrix A sub I, J, and then you have all of the different entries in that matrix. So two matrices are equal when they have the same dimension and all of their entries correspond to each spot in the matrix are all the same. So in this first example, if we have to solve for the matrix, really what we're just going to do is to look at the entries in the matrix we already have and say that the A11, which is row 1, column 1, has to be 2, since that's the entry that's in row 1, column 1. A12, row 1, column 2, would have to be -1. A21 would need to be -3. And A22 would need to equal 0. So be sure that you see that if you have two matrices, in order for them to be equal, they have to have the same dimension and the same corresponding entries. So if you look here, where you have this matrix and this matrix, those two are equal, even though they don't look necessarily the same, but you know that the square root of 4 is really 2, and another way that you could represent 1/2 is 0.5, right? And these are both 2 by 2 matrices. So if you look at this next example, this one you have a 3 by 2 matrix and a 2 by 2 matrix. So just by the fact that they don't have the same dimensions would mean that the matrices aren't equal. Even though this one just has that row of zeros, the different dimensions determines that they're not equal. So if two matrices have the same dimensions, you can add them together by adding their corresponding entries. So both entries that are in row 1, column 1, you add those together, row 2, column 2, and so on. And so if we look at this example, if we want to add these matrices together, we would add row 1, column 1 with row 1, column 2. So we would get 6. When we do -2 and 0, we get -2. 1 and 8 is 9. And -4 and -3 is -7. To subtract, we do the same thing. And again, you first need to determine if they have the same dimensions, because if they don't have the same dimensions, you can't add or subtract them. So here, if we're subtracting, 4 minus a -2 gives us 6. -6 minus 3 gives us -9. And 0 minus 1 is -1. When you look at C, we have a 3 by 3 matrix and a 2 by 3 matrix. So since the dimensions aren't equal, you can't add the matrices. So when we look at operations with matrices, if there's a number out in front of the matrix, we call that a scalar. And then what you do is you just multiply every entry in the matrix by whatever that scalar is. So in this example, if we have matrix A that they're given, and we have to find 3 times A, so 3 times A would mean that we just have to multiply every entry in our matrix by 3. So we would get 6, 6, 12, -9, 0, -3, and 6, 3, 6. So some properties of matrix addition and scalar multiplication, it really is probably what you think it would be. If you add A plus B, it's the same as B plus A. So when you're adding or subtracting or multiplying by a scalar, really all of your other algebra rules will hold for that. So when we look at this next example, two ways we can approach it. We could distribute this 3 first to each matrix, or maybe it would make sense to add the matrices together first and then to multiply by 3. So if I were to add these matrices together first, I would get 2, -2, 7, and 8. And then I would have to multiply each entry by 3. So then I would get 6, -6, 21, 24. And then sometimes you're going to be asked to potentially solve for a matrix. And so if you had to solve for matrix X, but you were adding A plus B, and again, they're capital, so you know they're matrices, you really do the same thing that you would do in algebra, right? If you had algebra and you had to solve for X, you would subtract A from both sides. And so X would just equal B minus A. And the same is true for matrices. So if we want to solve for X, and it says 3 times X plus A equals B, then we know that 3 times X will equal B minus A. So the first thing that we would need to do to solve for matrix X is we would have to take our matrix B, which is -3, 4, 2, 1, and subtract matrix A, which is 1, -2, 0, 3. So if you subtract those, we get -4, 6, 2, -2. And then to get rid of the 3 in front, we would have to multiply both sides by 1/3. So that scalar that we're multiplying our matrix by would be multiply everything by 1/3. So your matrix X would equal -4/3, 6/3, which is 2, 2/3, and -2/3. And that would be what your matrix X would equal. The other operation that we're going to talk about is matrix multiplication. And with matrix multiplication, it's a little bit trickier because we have to multiply rows and columns and add them together. So that's a little bit more of a process, but you can actually use that in solving more complex problems. So in order to multiply matrices, you have to make sure that if you're in your matrix A, here if you look, we have 3 rows and 2 columns. And in matrix B, we have 2 rows and 2 columns. And in order to multiply together, so if we have rows by columns and we want to multiply that in your rows by columns for your other matrix, the columns in your first have to equal the rows in your second. So if you look here, the 2 and the 2 are the same, so we can multiply them together. And your resulting matrix actually ends up being the outside dimensions. So when we multiply these together, we're going to end up with a 3 by 2 matrix. So 3 rows and 2 columns. I should have a little space there. So we'll have our 2 columns and our 3 rows. And if you think about the entries, this is row 1, column 1. So the way we're going to get this information, or the entry, is we're going to take row 1 from our first matrix, and we're going to combine it with column 1 from our second matrix. And it's almost like we do the dot product. So we do -1, this first term, we take -1 and multiply it by the first term here, so times -3. And then we add this next term, 3 times -4. And so then we say, well, the next one, we're in row 2, column 1. Right, so we have to combine row 2 with our column 1. So we'll have 4 times -3 plus -2 times -4. And then this other entry is row 3, column 1. So we're going to take row 3 with column 1. So we'll have 5 times negative 3 plus 0 times negative 4. And we'll simplify all this down. And so now if we're going into the second column, we're going to do the same thing. Let me take off these circles so we can see these a little bit better. So now if we go to the second column, we're still row 1, but now we're column 2. So you have to think we're going to combine row 1 with column 2. So we're going to have negative 1 times 2 plus 3 times 1. And then row 2, column 2 will be row 2 and still column 2. So 4 times 2 plus negative 2 times 1. And then in row 3, column 2, so we'll combine row 3 with column 2. So we have 5 times 2 plus 0 times 1. And then you just have to simplify. So you have 3 minus 12. So we would have minus 9. And then we have minus 12 plus 8. So that's minus 4. And then we have negative 15. And then on the other side, we have negative 2 plus 3. So that's 1. 8 minus 2 is 6. And 10 plus 0 is 10. So this matrix would be matrix A times matrix B. And when you're doing these, you do need to show kind of all these steps of what you're multiplying together to get each entry. So then here's just some properties for multiplication, and you can't just switch the order of multiplication and have the same thing. So if you want to do A times B times C, you can go in whatever order. But the thing is, if you were to multiply matrices, A times B does not equal B times A. So you don't have that commutative property for your matrices. So order matters in the multiplication. The identity matrix is just the matrix. It's like when you multiply a number by 1 and you get the same number. So in matrices, when you multiply a matrix by its identity matrix, the identity matrix just has the ones down the middle as a diagonal, and every other entry is 0. So if A is an n by n matrix, then the identity matrix is also going to have those same dimensions. So here, if you were to take this matrix and multiply it by the identity matrix, you would still get that original matrix. Same thing, because you're multiplying by the identity, you can actually switch the order and you can still get that same matrix. And so tying this back in with vectors, you can actually write vectors as a column matrix. So if you had a vector U, its components are U1 and U2, or that's like your A and your B. And if you wanted to add it to vector V, which has components V1 and V2, then you would just add their similar entries and you would get that vector addition. So here, if we have these two vectors and they're in matrix form instead of component form, if we want to do U plus V, we just add them together and we get 8 plus, or sorry, not 8 plus 6, we get 8 and 6. For part B, we want to do V, which is 6, 2, and we want to subtract 2U. So 2U would be 4, 8. And if we subtract those, we would get 2, negative 6 as that resultant vector. So in this next example, they give us matrix A, and at first it looks like it might be the identity matrix, but if you notice, this entry is negative 1. So it's not the identity matrix, but this is a 2 by 2 matrix, and they want us to multiply it with the vector V, which is a 2 by 1 matrix. So because these middle terms are the same, we can multiply these together, and our result will be a 2 by 1 matrix. So if we were to come up with what that 2 by 1 matrix is, and we draw our lines just to help us organize. So this is row 1, column 1. So if we're combining row 1 with column 1, it's the only column, we'll have 1 times 1 plus 0 times 3. And then row 2, column 1, we'll combine row 2 with column 1. So we'll have 0 times 1 plus -1 times 3. And so if we simplify that, we get 1 and -3. Right? So the question is that asks us to describe the transformation. So visually, if we think about it, remember vector v was 1, 3. It had the components of 1, 3. And so if we graphed 1, 3, our vector v would look like this. But now we're graphing, after we applied the transformation, we're graphing 1, -3. So that's down here. And this was a times v. So if we need to describe the transformation, we'll say that it was a reflection over the x-axis, right? Because our vector v just reflected over our x-axis onto that new vector. So what we find then with the applications is that when we have a system of linear equations, we can write this out as matrices, but we're not using the augmented matrix. We're actually writing it as A, which ends up just being our coefficient matrix. And then X is our variable matrix. And then B is what the solution side is. So we end up with 3 matrices when we're writing out the system of equations. And so this is kind of that example here. If you had that system of equations from this slide, and then you wrote it as matrices, you would have your A times X equals your B. So if we were writing this out, our A matrix, which is our coefficient matrix, would be 1, -2, 1, 0, 1, 2, and 2, 3, -2. Our X matrix would be x1, x2, and x3, because those are our 3 variables. And what happens is if you actually did matrix multiplication where you did row 1, if we did row 1 and combined it with column 1, we would get back to that system. And then we'll set it equal to the B matrix, which is that constant matrix of -4, 4, and 2.